Welcome, Mindsetters, to this grade 12 session of Learn Extra Live. Hope you guys are ready. You've got your pens and pads out and you guys are making notes. We have Heather in today who's going to be taking us through today's session. So tell us what's going to happen today.
We're actually going to be doing paper 3 today, guys, which is the optional paper. But really, don't go running for the hills, because even if you don't do paper 3, it's really good stuff. And it's got a whole lot to do with space and shape and whatever. So perhaps even if you don't do paper 3, but you'll end up getting into engineering or maybe into architecture, it'll stand you in good stead. So I hope that you stick around.
All right.
Okay.
So while Heather makes her way to the board, I'm going to tell these Mindsetters what they need to do. Mindsetters, as I always say, make sure you get onto the page. And make sure you guys keep posting and be active on the page. That's how you can stand a chance to win these awesome Casio and this Labial prize. And make sure, Mindsetters, you get chatting to each other, talk to each other. That's why this platform is there. It is for you guys to make sure you guys can connect. This is across the world. So make sure, Mindsetters, that you post. And chat to us. If you're lost anywhere, need help, let us know so we can help you. But for me, I'm going to now keep quiet, and this is where I head over to Heather. Heather, take it away.
Great. Okay. So, guys, this is where we are looking at paper 3. As I said, it is an optional paper. Some of you are very lucky that it is being taught in your schools, but even if it isn't, please, guys, try and follow, because it really just kind of reinforces the stuff that you've been learning in grade 9, 10, and 11. So what I want to do before we get into the grade 12 stuff is I want to do just a little bit of basic revision. So just remember that when you get to grade 12, you've got all of that stuff from grade 9, 10, and 11 in your suitcase, your skills. You can't ignore it. So before we launch, let's have a look and make sure you can do the grade 9 stuff. So do you remember that when you have a straight line, all right, or a straight angle of any kind, all right, if you can use your ruler and you can draw some kind of a transversal coming down to your straight line, then the property is that those two angles are called adjacent angles. They're next to each other, so that's a nice word for us to know, adjacent. But we know that when they form a straight line, this acute angle and that obtuse angle together add to 180. And guys, remember that in geometry, one of the things that we always have to do is provide a reason. We can't just say, we sucked that out of our thumb. We actually then have to give the reason, and the reason that we would kind of agree on is some angles on a straight line. And in this particular instance, we really are not sticky about being absolutely exact, as long as you give us the idea that you're adding up angles on a straight line. Okay, lots of people put adjacent angles on a straight line, and that's fine. We can see that you're talking about exactly the same body of theory. All right, the next little bit of information that I need to make sure that you know, and of course this is something that comes up in trigonometry, not only in geometry, is, are you aware that when you take a triangle, any triangle, we know that A and B and C, all of them together add up to 180, and of course our reason for that is some angles of a triangle. And we don't have to say anything more than that. Right, moving on to the next body of theory, which is this guy here. And of course, it more or less links up to there. Okay, so what we really want to be able to say is that, can we recognize that when we have a triangle, notice that if I draw my triangle, but I take one of the sides and keep on going using a straight edge, then this angle outside here, all right, is what we call the exterior angle of the triangle. Very, very useful in trigonometry, especially in those situations where we're trying to work out the size of an angle with angle of inclination. We know that the exterior angle is equal to the sum of the other two. So in other words, if this chap outside here is 120 degrees, we would know that A and B came to 120 degrees. They're not necessarily equal to each other. In fact, in very few cases are they equal to each other. But somehow they would add to 120. And our reason for that is exterior angle of a triangle. Okay, I'm sure you're looking at this and saying, this is so easy. All right, and then the last little bit of information, and of course this comes up a lot in analytical geometry as well, is that when we have a pair of parallel lines, all right, so I'm going to highlight the fact that these are parallel, all right, and that has been given to me by the fact that we've got these arrows, okay, going in the same direction. When they are cut by a transversal, all right, any line coming down, then we get 3 different types of angles formed. So our alternate angles, and of course that is our Z shape. So it is said that this angle here at D is going to be the same as the angle size there at F, because can you see that if I were to trace them out, they would be in the Z formation. All right. Secondly, corresponding angles. Now let's try another color. We don't want to make this a little bit too busy, but if we were to take this size here, can you see I've used a F formation? Then this angle here would equal this angle here because they are in a corresponding place. And lastly, co-interior angles. Now let's just extend a little bit down here. And remember that if I have got parallels and I take this angle inside there and this angle here, then I would be able to claim that X and Y together add up to 180 degrees because they are in that U shape. All right? And so that is when co-interior angles are supplementary. Okay, supplementary meaning adding up to 180, and it's because I've got parallel lines. Okay, so that was just a quick whip through the theory that you need to be able to build on from grade 9, 10, and 11. So let's move on to circle geometry. Now, I'm almost certain that as you are viewing that from home, those things don't look circular because somehow this pixelates and distorts, okay? They're not meant to look oval. They're meant to look circular. Okay, so just imagine in your head. All right, so again, we can't go forward until we've got the terminology. So first of all, and of course this is also kind of notation and vocabulary that you need in analytical. Of course, when you've got a circle, then we automatically have the line going through from the one side to the other, passing through the center is our diameter. Then, of course, any line, okay, radiating from the center to the circumference edge is going to be the radius. Then, another thing that we need to know is that any line going from one side to the other is called a chord. Okay, many people call it a chord, okay, but that's just badly pronounced. It's a chord, okay, and a diameter is a special case of a chord. It just goes through the center of the circle. And then, can you see that if I take my circumference and I just draw from one point to the other and I go around that edge, now what I've done is I've split my circle into a that piece and a that piece. Then that piece there is called an arc, that curved piece, and this piece is also an arc. Now notice that in the picture, because this is the shorter distance, this is called a minor arc, okay, minor meaning less, and this one is called the major, meaning it's bigger. And lastly, what we also need to notice is that if we have a segment, it is that piece there. So if I have a circle and I'm talking about that piece there, then that again is called the minor segment. Okay, and then the other one here would be your major segment. Okay, and if you had the chord actually being a diameter, then these two segments would be equivalent. Okay, all of that, now we can get into the actual theorems. Now, guys, if you are in the government, paper 3, proof of these theorems is actually to count about 5% of your paper. So it is worth learning the proofs. I'm not going to go through the proof of Theorem 1. I'm just going to show it to you. But when E.T. takes over after the break, he's going to show you how to prove Theorem 2. So we're going to do some proof and some application. Okay, the first theorem states, if you have a line drawn from the center of a circle, perpendicular to a chord, it bisects the chord. Now, all of these statements actually are reasonably to see. You can actually look at it and intuitively see that it's right. They say, if you have a circle and you have a line coming from the center of the circle, and you know that it is perpendicular, so that's the given condition, all right? You know that it's perpendicular. Then, as a result, you can deduce that these two pieces are equal. Okay, it seems reasonable. Now, the converse of that theorem, now converse just means and vice versa, says that if you have a line coming from the center to the midpoint, then it must be perpendicular. Now, I want to just skip a little bit and go down and show you what this actually means. Let's just say I've got a circle and I've got a chord and I've got a line coming skew. Can you see that there's no way on earth, even if I'd drawn that circle perfectly, that I could claim that this piece was equal to this piece? What is going to make those two pieces equal is the fact that if I actually come down at a 90, then that piece would obviously have to equal that piece. Okay? Does that make sense? It's kind of intuitively, that's what we expect. Okay, I just want to quickly take that away because I need to work on the previous slide. Okay, so how does this get applied? Well, let's have a look at the picture. It tells me that O is the center of the circle. PT, so from P to T, it's equal to T to V, and those are both 6. So I'm going to fill that in as a 6, and I'm going to fill that in as a 6. All right? Please notice that the way that we indicate that two sides are equal is with equal bars on them. All right? Even if I was in a triangle, if I made that and that, I would be indicating that those two sides are equal to each other. All right, they tell me that from O to T, it's x units long, and from T to R, it's 2 units long. So now I'm almost certain that you're sitting there saying, how is that possible? It's not looking to scale. That's correct. It doesn't look to scale, and you must beware that in all of these problems, you cannot go and measure the length, okay? They want you to find x. So you can't just pick up your ruler and measure it and say, oh, I know, x is so big, okay? You actually have to go and calculate x. All right, now what was that theory again? Remember, it said that if we come down and we know these are equal, then we know that that angle there is 90. So my theory is going to tell me that OTP, that angle, OTP, is going to equal OTV, all right, and it's going to be 90 because of this theorem, okay, that we have the line coming from the center to the midpoint. And again, you always have to tell them why you've said what you've said, right? So now we know, guys, that this is a 90. And now from here on out, oh my word, it's just going to be an application of what you learnt in grade 8 already. So you've got to think all the way back there. We've now got a right angle triangle. So let's have a look at that right angle triangle. What have we got about it? We know that that's 90. We know that that's 6. Okay, now let's go back. We know that that little bit there is x. Okay, now remember we're solving for x. How long is this bit? Now this is a very important bit of deductive reasoning. Can you all see that that bit there is a radius? That bit there is a radius. And that's the property of a radius, is that we know that in this picture, from O to, Whoopsie, we are getting an overlay, so let's just clear that down. So we know that from O to P, it is the same length as from O to R. OP and OR, those are equal radii. So how long is OR? Can you all see that OR is going to be the sum of x and 2? So therefore, OP is also going to be x and 2 because of equal radii. Okay. Hope I'm not rushing you too much. So this now means that I'm going to get that this is x and 2. And I think now you can see that what we're solving for is x. So by Pythagoras, alrighty, we've got that the square on the hypotenuse, which is x and 2 squared, is equal to the sum of the squares on the other two sides. Goodness, that just disappeared. Okay, so it's going to be x squared and 6 squared. So this, guys, is by Pythag. Okay, again, I'm giving credit because that's a geometrical reason. So I'm going to get, squaring this out, x squared plus 4x add 4 is equal to x squared add 36. And of course, you're going to get our x squareds are going to cancel. So we're going to get 4x is equal to 32. So x would be 8. And so going back to our picture, in order to solve it, x would be 8. Right, I think that that's a nice application of our theorem. And so we now need to move on to the next theorem because there are 9 of them in total. So our next theorem, okay, but I've just been told that I need to go to an ad break. So I'm going to leave you there, and then E.T. will be taking over immediately after this break. Ty, take it back.
All right. So mindset is on that point. Make sure you guys stay tuned. Do not go anywhere. Make sure you stick around. And for those of you who keep asking, how do we get these prizes? All you have to do is be active on the page. Chat to us, participate with us during the show, and make sure you talk to us. And that's as simple as it is. Then you can get these awesome prizes sent to you, this Casio calculator and this labeler. And on top of that, I just want to send a quick shout out to Liberty and thank you for sponsoring the show. But for now, we're going to see you after this break. Welcome back, Mindsetters. I hope you had a nice little break. You went to the bathroom, you went to go get snacks, whatever you needed, so you need to pay attention right now. Because we've done a little bit of a magic trick, you know us, we always try to keep you on your feet. But now in studio, we've got Iti, who's going to be taking us to the rest of this segment. Then we're probably going to have Heather come back in the third segment. So make sure you have your pens, pads out, and you make notes. Mr. Iti, take it away.
Thanks a lot, Ty.
No problem.
Greetings to our viewers at home there. You've heard Heather mention that there's a few theorems that we are going to pick and choose, and some will prove, some will not prove. And I'll go straight into one theorem that I would like us to prove. It's very important. It's talking about the central angle, which is now an angle. If you look at the picture that I have here, I've got a circle that is centered at point O, right? And the points A, B, and C are on the circle. We say, let's take a pen there. We, earlier on, Heather specified this as the arc in a circle. Now, we're saying this arc is subtending an angle on the circumference, for instance, and it's also subtending an angle at the center. Okay? So we say that angle that is in the middle, which is at the center, is called the central angle. So let me reserve the word subtended angle for this case, for an angle that is on the circumference. So this theorem says the central angle is double the subtended angle. It's twice the subtended angle. So this theorem, therefore, can be proven. Notice the structure when I'm proving. We were given the following information. A circle centered at point O and points A and B on the circle such that arc AB subtends angle ACB. That is the given information, and you are required now to prove that AOB, which is the central angle, is twice ACB, which is the subtended angle. What kind of construction can we come with here? This is the kind of information that you add, to sort of make it convincing or help you with a proof. So in this case, if we take a line that cuts, cut through O and C with a line, let's say a line that will then do this. Okay. Okay. So now what you're having there is that this line that I've introduced is actually describing two triangles. I now have, if you can look at it, I now have two triangles, triangle AOC and triangle BOC. So if I look at those triangles, earlier on Heather specified that an exterior angle of a triangle is equal to the two angles that are inside, the two opposite interior angles. So in this case, let us, in the construction, also specify that, let's say we name this angle X, and we name that one Y. So let ACO, angle ACO equal to X, and angle BCO equals to Y. Right? If we have that, and let's go back to the triangles that I was talking about. An exterior angle will be equal to the sum of the two angles inside. So this means if you look at, okay, now let's go to the structure before I make a lot of statements without giving reasons here. So if we say angle ACO equals to angle, was that CAO, CAO, and they are both equals to X. I will have to give a reason for that. And earlier on, you had Heather mentioned that the radii have got the same dimension. So basically, if you have a triangle and you've got two sides that are equal, the angles that are opposite to those sides are also equal. So what do you call that triangle? We call it an isosceles triangle. So I will just give a reason as isosceles triangle ACO. That triangle is isosceles, therefore the base angles must be equal. Right? That's just one. If I go to the other triangle, the exterior angle there, sorry, before I get to that, that's OBC equal to OCB. OBC. And they are both equal to Y. The reason is the same, but it's an isosceles triangle that is BCO, let's say. Okay, so we know that for an isosceles triangle, the base angles have to be equal. So where am I getting with this? If I then specify a point on this line as, let's say, P, okay? I'm specifying that because now I want to name an angle at that point. Or maybe even to make it easier, I could say that's 1, that's 2. So what we then have is that O1 as an angle is equal to 2x. Again, sum, hang on. That is now exterior angle equals to sum of opposite interior angles. Okay, so that's the reason why you added x and x, in this case because they are equal. So that is x. So you added x and x to get your O1. What about O2? All right, let me extend this page. O2 becomes 2y. The reason is going to be the same as that. This is now for, I think I need to specify the triangle there. In this case, it's for triangle ACO. In this case, the reason is the same, but for triangle BCO. Okay. Now that you've got these two angles specified like that, notice that our central angle is the sum of O1 and O2. If we say angle O, which is at the center, I think we said AOB. Just check that. AOB, yes, it's a central angle. AOB is equal to, okay, we said earlier on that O1 is it's equal to 2x, and O2 is equal to 2y. So, but AOB is equal to O1 plus O2. That adds up to 2x plus 2y. If you take out a common factor of 2, you've got 2 into x plus y. That's interesting because now, if you look at your subtended angle is actually the sum of the two angles, x plus y. So therefore, this means that what we have is AOB is equal to 2 times our subtended angle is ACB. So we've proven the theorem using those steps. So there's no need for reason here, precisely because it's simple algebraic steps. Okay, I have proven this theorem. I would like to jump to one question that will require us to apply this. And if I can just move to that quickly. All right, one more. So I've got this question here. Look at this figure. You've been given a circle all the way there. You've been given this circle. And on top of that, you've been given that R1, point R is this one here. And you've got a small angle there, which is 1, and you've got 2 and 3. Just writing them bigger. All right, so they are telling you that R1 is equal to Y, and O1, which is the central angle. The central angle is given as Y, and now they say to you, express X in terms of Y. Again, what you'll notice is that this triangle here has got a bit more information. You've been given that this side is equal to that side. We go back to that deduction we made about an isosceles triangle. This is an isosceles triangle. This means that the base angles are equal. So if this is Y, that is also Y. Okay, so if you have that, again, they're all interlinked. P1, this is point P here, and this is 1, and that's 2. P1 is now an exterior angle of the triangle PRT. Okay, let's write that statement. P1 is then going to be an exterior angle, which is equal to 2y. The y you have here and the y there, they add up to an exterior angle. This was mentioned earlier on by Heather. So you then have to give the reason anyway. You're going to say exterior angle of a triangle. Okay, that's equal to the two opposite interior angles. So you can actually complete that. But this could be enough. So there you are, you've got P1. If P1 is 2y, and you also know that the central angle, which in this case it's O1, or your x is supposed to be 2 times P1. You write that statement. What's that? O1 is equal to x, which is twice P1. Okay, so again, central angle equals to twice your subtended angle. Okay, that's your reason for making that statement. But then you can go back to the first line that said P1. Where you see P1, you can put 2y, and you do exactly that. Then you have that x is equal to 2 into, where you see Py, you put 2y. Then your x is actually 4y. Right. So that's the first part of that question. If we move to the second question, it says if TQ is equal to TR. So where is TQ, where is TR? So from that point to that point is the same as from that point to that one. So in other words, if I can just highlight it like that, that is equal to that one. Right, so if that is given like that, and you are also given that the angle x is equal to 120 degrees, calculate the measure of first question of y, and then the second one is R2. So y, remember we already have an expression which says, that's the first part. It says, where you see, where x is, can be expressed as 4y. Therefore, where you see, you just have to rearrange that equation so that it gives you the y. So your y will therefore be equal to a quarter of x, which is a quarter of 120. That is equal to 30 degrees. You have answered the first part of that. And now the second part says find R2. R2 is now an angle that is sitting hidden over there. I'm going to erase this for now. R2 is an angle that is right there. It's angle ORP. What do you know? You know that this side is equal to that side, so it means that that angle is going to be equal to that. Now, let's make all these statements with reasons. Okay, I'm going to extend the page here to do this question. Okay. So what we're having is that the statement we made is that Q, or let's say PQR, is equal to QRT. PQR, angle PQR is equal to TRQ. TRQ. And our reason for that, we've got an isosceles triangle. Isosceles triangle, which triangle is it? You have to specify that, TQR. TQR. Okay, so that's just one point to mention there. Where am I going? So we're actually looking for an angle that is much hidden in this complexity there. And one thing for sure is that if they gave us that x is 120, we also have an isosceles triangle there. Thereby, okay, let's do that. OQR is also isosceles, which means the base angles are going to be equal. Okay, OQR is going to be equal to OQR is going to be ORQ. This we mentioned earlier on. It's isosceles because of the radii. Okay, radii are equal if your triangle is from the center to the circle. All right, so if that's the case, then it means that if you have 120 as the angle in the middle there, angle X, then you are left with only 60 to make up the 180. So if you are going to make up the 180, you may as well say, okay, let's go. You may as well see that angle as 30 degrees and 30 degrees. Right? And another one to pick up on is the central angle. Okay? We said the central angle is twice that, which means we know this angle over there. All right? If we know that angle to be, what did we say it is? P1, that's 4y. So that is 120, let's say. X is 120. What did we say? We said X is 120. Oh, then it means that this angle over there is equal to 60. Okay, so now you already have 60 there, and you've got 30 there, 30 there, which means what is left is to find this angle over there. All right? All right. Then I don't think I have enough time to cover all of it. I'll leave it at this. Heather will basically finish it up, right?
Okay, no problem.
All right, great.
So on that note, mindsetters, make sure, because the page is still pretty quiet, and I'm just wondering, like, hey, where are my mindsetters today? I know you guys think it's just paper 3, and you're like, I'm not going to do. Make sure you get your friends to do it, because the thing is, the whole point is to expand your mind. That is the whole point of mindset. So guys, get on your page, get your friends to get on the page and chat. So you can win these awesome prizes for your exams and for just home use. But make sure, guys, you keep talking to each other. That's why this platform is there. But for me, I'm going to tell you guys to see you after this break. Welcome back, mindsetters. I hope you had a nice little break. You went and did whatever you had to do. You went to the toilet, or you went to whatever you had to do. Make sure you got some snacks, some water, something to keep you refreshed, so you can pay attention for this next segment, because this is our last segment. So make sure you have your pens, pads out, and you're making notes. So I'm going to hand over to Heather. Heather is going to continue the show. Take it away.
Okay, thanks, Ty. Okay, guys, so what E.T. was doing was explaining that second theorem, which is so important. But now that he's done the kind of proof of it, I want to just make sure that you can see that this theorem can actually have a couple of different applications, actually visually. So we need to be able to recognize it. So let's just have a look at what E.T. was saying. Do you recognize that he was saying that when you have an angle hanging to the center, and then that same arc hangs an angle to the circumference, then that one at the center is double the one at the circumference. Okay, now that's the picture that he presented to you. But now if we have a look at these next cases, can you see that once again we've got an angle subtended or hung to the center, but now just a little bit different. Can you see that here the one to the circumference was like directly above it? Okay, so look at this. It's kind of directly above it, and that's how we prove it. If this is 2x, that one's x. But now can you see that here, this one is going off to the side, but the theory is still exactly the same. As long as they're hanging off of the same feet, so in other words, can you see that this piece here, the arc, is subtending to the center, that one is going to the circumference, that one there is automatically going to be double that one there. And whether it's subtended skew to the right or skew to the left, if this one is, let's say, 120, then this guy here would be 60 automatically. And also, here what they tend to do is they tend to be a bit sneaky. They tend to turn the picture upside down. Well, so what? If I had to turn this back again, can you see again that this is the angle subtended to the center, and that one there is the one that they're talking about at the circumference. Now there's a third case. Can you see that in this particular case, my arc that's doing the subtending is actually the arc of the semicircle, and the angle at the center is 180. It's a straight angle. So we know that this one is actually double that one, and so if that's 180, that one has to be 90, which gives us a lovely body of proof that if you ever have a semicircle, all right, and you have an angle coming off that semicircle, then that one there is going to be 90. And sometimes that's useful in analytical geometry. But of course, it has to be that this one here at the center is 180 degrees. Now, the last one, which is the fourth case, which is the one that's quite difficult to see, is if I've got the arc, the major arc doing the subtending, then this reflex angle here, this one here, not this one here, so this one is 2y, it would be double this guy up here. But this reflex angle is going to be double that one down at the bottom. So if that's a 2y, so let's say that this is 240, then this one here would automatically be 120. And how do we actually substantiate it? We always just say angle at center twice angle at circumference. Okay, moving on to the next actual theorem, which you don't have to know the proof for. The third theorem actually says the following. If you have an angle subtended by an arc, AB, to the circumference, and we subtend a second angle from those same 2 points, all right? Then it says that these two angles are going to be equal to each other. Now, likewise, these two are going to be equal to each other. Now, a lot of candidates refer to this as the bow tie theorem, because you can see it obviously looks like a bow tie, all right? Other candidates refer to it as the cat's ears theorem, okay? But can you see that they definitely looks like cat's ears? But if you had to actually write that as a reason in your exam, you'd get it wrong. Okay, that's what it looks like. But the reason for this that we actually give, if we ever use this, is going to be angles in the same segment. All right. Now, I do want to just point out to you 2 errors that lots of candidates make. My circles are not perfect because they say that you have to be 100% crazy. Do you know that time? 100% crazy to draw 100% circles. Okay.
That I've never come across, but
Okay,
makes
it's
sense.
True.
Yeah.
It's true. Okay, so if I have what I've just been talking about, all right, and if I have this situation, all right, I want you to look at this with interest, all right, very subtle difference. All right, all of these points, A, B, C, and D, are on the circumference edge. Now, this angle here would equal that angle there. This angle here would equal that angle there. And my reason would be angles in same seg. All right. Whereas this one, can you see, although it almost looks like a bow tie and it almost looks like cat's ears, the very, very big difference is that this one is subtended to the center, that one is subtended to the circumference, and so whatever this one is, 2x, that one there is going to be x. And that is an application of angle at center 2 times angle at circumference. Okay, right, we're now moving on to the next body of theory, which is all about cyclic quads. Okay, now, this is a new word for you, cyclic. All right, cycle. Doesn't want to actually take my pen, but let's take cyclic. All right. Cyclic means that you've got a quadrilateral with all four corners on the circumference, on the circumference of the same circle. Okay, not different circles, same circle. Okay, now this theorem is actually quite fascinating because it claims that if you've got a cyclic quadrilateral, the opposite angles add up to 180. Right, now I want you to dig deep into your grade 10 syllabus where if you have a special quadrilateral called a parallelogram, all right, what is true about a parallelogram is that the opposite angles are equal. So let's say that's 70 and that's 70. Then this would be 110 because of co-interior angles. And this would be 110 because of co-interior angles. So can you see here the opposite angles are equal? Okay, this is something a little bit more special. If you have a cyclic quadrilateral, they are saying that the opposite angles add up to 180. Not that they are equal, but they add up to 180. Okay, so what we're going to do now is we're going to go down and we're going to do that important thing which is called a proof. Okay, so please notice that in a proof, you get given a certain picture with certain elements in the proof. So what we've got is a quadrilateral ABCD. It's drawn with all 4 points on the circumference, and we've got a center at 0, okay, or O. We want to prove that A, let's say, and C add up to 180, or alternatively, ABC, which is this angle, and this angle, we want to prove that those two angles add up to 180. Now, do you remember earlier when Ty was proving something, he said that sometimes it's important in order to facilitate a proof that you do a construction. Okay, now a construction is something that often gets put into a proof, but never into a rider. Now, Ty went and did a rider afterwards, which is kind of the application of the theory. So what I need to do, sorry, I said Ty.
I was
didn't
wondering,
I?
like, okay.
Okay, E.T.
Itty.
Okay, sorry.
I was like, okay, I
I've
did
been
the
on
rider.
holiday for too long. Okay, all right. So what you're going to do when you do your construction is you're going to actually join A to O, all right, as we have, and O to C. All right, and when you do a construction, we normally dot it. So we join A to O and O to C. Now, what I would like you to be able to see is that I have now created an angle to the center. So this angle here, all right, I hope that you can all see that, is going to be related to that one up there. Can you see that AOC is going to, let's say, be 2x, and ADC is going to be x. Why? Because of that body of theory that we had from previously Theorem 2. So what we are going to do is we are going to say that AOC is double, okay, ADC, and that's because of angle at center twice angle at circumference. And I'm going to chivvy along with this quickly. Then that reflex angle I was talking about, this angle here is 2y. This angle here is y. So the reflex AOC is going to be twice ABC. So reflex AOC is going to be twice ABC. And heaven help you if you ditto in an exam, but I'm allowed to ditto now because I'm running out of time. Now, guys, can you see that what I've got at that central angle here, all right, is a 2x and a 2y. But what do I know about the 2x and the 2y? Can you see that that's a whole revolution? So what do we know about 2x and 2y? We definitely know that that comes to 360 because it's a revolution. Okay? And finally, we can therefore say that 2x plus y comes to 360 just by taking out my common factor. And so that means that my x and my y come to 180. So therefore, I've proved that my opposite angles add up to 180. Okay, I've been a little bit slapdash in that proof, but hopefully I've got the idea through to you that this 2x would be double that one. This 2y would be double that one. That 360 degrees, all right, is going to be angles around a point. And so if those two together add up to 360, then those two add up to 180. Right, this has got huge impact on when we do problems, because the minute that we get something along these lines, okay, and it doesn't matter where my cyclic quad is, all right, if I give you that this is 30 degrees, doesn't look like it, but still, if I give you that that is 30, then I can automatically say that that one down there is 150. If I give you that this is 40, then I can automatically say that that one across is going to be 140. And so if you know your theory in paper 3, it's so wonderful to be able to apply, and these puzzles kind of just fall into place. And you can see that I'm really passionate about this. I really, really love paper 3. Does anybody on the page love paper 3?
Yes, we actually do have a couple of
we
people. I was
do?
also surprised, yeah.
Oh, good. Oh, good. Okay. So they share my passion.
Yes, they do.
Okay.
Greatly.
All right. So I think, Ty, that I'm done. So if you want to close up the show for us and
All
just
right.
tell them that we're going to do paper 3 again next week.
Okay, awesome. Because actually, we have one of our viewers, by the name of Kashifa. She's always on the show, and I always say hi, Kashifa. She actually says, "Wow, thanks for explaining so much of paper 3 to us. In our school, only 6 students actually do paper 3, and we've never had a teacher explain it to us." And she says, well, the teacher usually just says, you know what, guys, you have to know from here to here in the book by the end of the semester. So for someone to actually help us learn it, help us understand it more is such a help. So she's just saying thank you so much.
It's
and
a great
on
pleasure.
that note, I'm going to say, guys, see you next time. Make sure you stay tuned and keep chatting on the page. But cheers.